If we continue to use this coronavirus protein as an illustration of protein structure, we can see a pretty good summary of the things we've talked about so far. Alpha helices are these spirals that form up columns that are used as structural elements. And up here in the yellow, we can see beautiful examples of beta sheets. These strand interactions right here are going to be all anti-parallel. We've got a very clear anti-parallel direction of those arrows. So I looked through this and I don't see any parallel interactions, and I'll have to show you one of those in class because they're pretty common too. So we've done the heavy lifting here for secondary structure, but you can see besides the purple and the yellow, there's still lots of parts of the protein that are remaining. And it's all this kind of thin spaghetti type structure. And for instance, let's take a look at this particular structure right up here where we have a beta strand coming down. It turns in sort of a hairpin and comes back the other way in another beta strand. That's a special structure called a turn. What about all this other sort of seemingly random looking stuff? These are called loops, and our next part of the notes is going to be turns and loops. So beta turns are a very special, specific type of structure. They're sometimes called beta turns. They're sometimes called beta bends. I tend to use the term turn rather than bend. And it's a very specific structure, like I said. It can only ever be between two anti-parallel strands. It's the only place you can have it. And the reason is because that. So let's get into what a turn is. A turn is always exactly 4 amino acid residues. And we can see them right here. We'll go ahead and write them out. Here is the alpha carbon for amino acid number 1, and it is having an NH over here, a carbonyl over here. Here is the amino acid alpha carbon for number 2, and down here is 3, and over here is 4. So it's always exactly 4. Now, the first and fourth are always hydrogen bonded to each other. In fact, they're double hydrogen bonded. We can see a beautiful standard hydrogen bond here and there. These are carbonyl to NH, just like we see all up and down the beta strand. In fact, what we can say is that these hydrogen bonds that I just put the dots on, those are essentially an extension of the beta sheet. Now, it's in the second and third position where we see something unusual. I'll put it up here. The second and third position are right here and here, and those are where the actual tight turn is, where we turn around and go in a different direction. And those have to have some unusual angles. They have to either be highly flexible or they have to take on some unusual angles. And because of that, we would say that position 2 or 3 often, not always, but often are either, can you remember which is our most flexible amino acid? It's the smallest side chain, glycine. And it turns out that, ironically, proline, which is the least flexible, is also often found in turns. And the reason for that is because it forms unusual angles. So that's what beta bends or beta turns are. They're pretty simple, and we can call them part of secondary structure. We can call them a connector between secondary structure, but they're only ever found between these anti-parallel strands. That doesn't mean you have to have a beta turn between 2 anti-parallel strands. You can have other types of structure connecting them as well. So that's what a beta bend is. let's move on toward the bottom of the page here. Let's say we have a schematic here of a beta sheet with two anti-parallel strands. Perhaps we would call this a turn, and that would be a very fine thing to do. Alternatively, as I mentioned above, we could connect these two strands by having a much longer and irregular structure that is somewhat random in its structure. That's called a loop. And loops can be anywhere from, I guess we could say, 2 on up to huge. It could be 20 or so amino acids long. There's no set length. There's no regular structure. There's no repeating patterns. It's basically structure that connects alpha helices and beta sheets to each other. Let's take a look at the structure we saw at the beginning of this video. This protein has lots of beta strands, it has lots of alpha helices, and I mentioned it even has a turn, clearly a turn right there. But what about if we have to connect a beta sheet and an alpha helix? Like for instance, over here you have an alpha helix and a beta strand right here. We have to connect those from time to time, and here's a good way to do that. This part right here is a little loop. It's probably about 7 or 8 amino acids long. There's no regular structure, and it is basically just connector. Here's a beta strand, a loop, and that's connecting to another beta strand that is not actually physically associated with the first beta strand. So this is how it works. The core structure of proteins is made up of alpha helices and beta sheets. Everything else that you need to connect those to each other is going to be turns and loops. That's a little bit of an oversimplification, but it's good enough for what we need to do to understand proteins. Let's finish that as the end of secondary structure.